All right, this video is going to talk about some applications of solving systems of equations, and we're going to talk about it in two different ways. First of all, notice that City A has a population of 300 and is growing at a steady rate of 20 people per year. And we're going to sort of apply these methods of why would we use systems of equations. Well, City B also has a population of 20, right? But it's growing at 10% each year, right? So they're both growing in population, but the real question is, will the cities ever have the same population? Right? Again, if we're going to grow at a steady rate, we're talking a linear rate. So again, the population would be equal to 300 people, but again, growing at 20 people per year, right? If we let X equal the years. Right? But on the other hand, the population of this city, right, is just 20, so they're starting out much smaller. But again, they're going to grow, right, at 10% each year. Well, 10% is more of a multiple. So actually, I'm not going to add. What I'm going to do is go ahead and say that it's going to be 100% of the population plus 10% more of the population every year. It's going to be an exponential growth, which makes me think that, yep, it should catch up, and it should catch up pretty quickly, right? This would be a great opportunity, will the cities ever have the same population? If so, when? If not, why not? This would be a great chance since they're both solved for P. We could do substitution, but I'm thinking this would be a great graphing problem. So let's hop onto our calculator. Let's go ahead and clear out one of these old problems here. And let's type this thing in. So again, we're going to start with 300 people on our first population. Oops. And then we're going to go up here. And we're going to add on, right? Again, if we remember from our previous problem, 20 people per year. So 20x. Now remember, make sure you're using your variable button here. 20x. In the next problem, again, we started with 20 people. But again, we're going to multiply by 100% plus another 10%, right? 1.1 raised to the x. And if we go ahead and graph this thing, now notice the first population is going to be 300 and only getting larger. So immediately I'm going to go ahead and hop onto my window. I'm thinking we've got to start in year 0. Let's go for about 20 years just to see what would happen. And then for the y values, well, I may as well start at 0 for the minimum, though we know we're not going to really look below 300. In that case, though, let's go ahead and see if maybe we get there by the time we get to 600. And just for help, we'll maybe count by hundreds just so we can see that on the graph. There's our linear line, and it looks like it's going to take longer than 20 years. But notice that red line's starting to curve. So even though the blue line's going up, they look like they're getting farther apart. Let's go ahead and expand our search out a little bit here. Instead of 20 years, how about we look at 50 years? Right? Well, now it looks like we're definitely going to catch up, right? Our red line's taken off. They're getting a little closer together. If I could imagine that blue line also sort of going up there. So again, this is taking a little bit of a search, but that's okay. Let's go ahead and see if maybe when we get to 2000, I'm just going to put a fairly large number in there. And it looks like there we found our intersection point, right? So let's go ahead and find that point. Remember, to find an intersection point on your calculator, you're going to press second, trace, or go to the calculate button, right? We want to find an intersection point, number 5. It's going to ask us a couple of questions. First of all, are we on our first curve or our first line? Well, I'm definitely on the blue line here, y1. So I'm going to press enter. Now, am I on the second curve? Well, yep, I'm definitely on the red one. I'm on y2. So I'm going to again press enter. And now they want us to go over to make a guess. Now you'll notice there's really only one intersection point on our screen, though there would have been another one off to the left here. We just don't need to really go into negative years. But again, what they want you to do is put your intersection point near the one you want to find. So I want to make sure I'm closer to this intersection on the right than I would be to wherever that would be on the left. So let's go ahead and press enter there. And it looks like we get a nice answer. And I'm going to go ahead and take a quick snapshot of that. Right? I'm going to get a quick answer here. We'll put that on our screen. Whenever you're solving by graphing, we definitely want to show our work. But it looks like, will the cities ever have the same population? I would definitely say yes. they will. And it looks like, again, the intersection, if so, when, well, x, remember, was our number of years. So sometime during after, right, 42 and a half years here or so. So about 42.514 years. And again, if they wanted us to round to the nearest whole year or something like that, we could say yes after about 43 years, right? It's at 42, we still would have been just short. But at 43, we would have been past the point of intersection. So again, solving by graphing is a great way to do that. Another sort of typical system equation problem is what we call a break-even problem. In business applications, when the cost for producing X number of items equals the revenue, right? The cost being the money you spent, the revenue being the money you're bringing in. So basically, when your profit is exactly zero, we're not owing money, but we're not gaining money, right? But when the cost equals the revenue, you've reached what we call the break-even point. So looking at this example up top, there's a shoe company that invests $300,000 producing a line of shoes or footwear. They're also spending $5 per pair. So again, $300,000 is just sort of their flat cost, but they're also spending $5 per pair of shoes for the materials to make the shoes. But now we're going to sell those shoes for $60 a pair. How many pairs must we sell in order to break even? You might be wondering, well, why do they pump that cost up so much? Well, let's take a look. The cost is going to be the $300,000 plus an extra $5 per shoe. Revenue, again, $60, right, for a pair of shoes. And so if we set those two things even, now you could easily solve that by graphing, but this is a good linear equation. I'm thinking we can just do the work ourselves here. When the cost equals the revenue, right, we can subtract and divide, right? We'll find out that X equals, well, let's hop onto that calculator again. Only this time I just need to calculate my number. 300,000 divided by 55. And we are 54.55 or so, approximately, right? So how many pairs of shoes must be sold before the business breaks even? Well, we rounded up, so we're in good shape there. I would say that 5,455 pairs, right, need to be sold in order to break even, right? And again, we're going to technically have made a little bit of money there, but again, that didn't come out to a nice solid number, so we're just going to have to go with that. Now, I don't necessarily need to go find the cost or the revenue, but if they wanted me to find how much money would that have cost me, or how much money would we have brought in, when would the profit have been zero, right? The cost minus the revenue, or the revenue minus the cost, either way you want to put it. When that comes out to zero, well, here's where it happens. What happened, or what's more important, is how many pairs do we need to make? What should we tell the factory to do, right? So there we go. Again, there's just two good examples of applications of both solving by graphing and substitution. If you have any questions, make sure you talk to your teacher. Otherwise, have a great day.